Good afternoon, everyone. I'm Heejin Park from Purdue University. Today, I'm going to introduce the paper of StreamBox-TZ, a secure stream analytics at the edge with TrustZone. This work is joint work with Zhai and Professor Felix from XL Lab at Purdue and Professor Long from Northeastern University. So these days, a lot of IoT devices are widely deployed in many areas and generate a large stream of telemetry data. For instance, millions of power samples are produced in the area of smart grid. To process this large stream in time, edge processing is now emerging, which cleans and summarizes data stream and report the result to the cloud server for deeper analysis. In general, ARM processor is a popular choice for edge device due to its compelling performance at low power. It normally has 4 to 8 cores with several gigabytes of DRAM. While the edge processing is compelling, it has many security threats. First of all, its attack surface is wide, as the software stack on the edge is large, complex, and potentially vulnerable. Second, the edge device is high-value target, as the data is aggregated from the multiple sources. Moreover, edge device shares common IoT weakness, such as lack of professional supervision, weak configuration, or delayed security updates. These make edge device even more vulnerable. So in our scenario, sensors and cloud are trusted, but the edge is untrusted, as its OS can be compromised. For example, the adversary can compromise the OS by exploiting the vulnerability on the user kernel interface locally, or the similar attack can be done remotely. We assume the powerful adversary who can control the entire edge OS so that they are able to access confidential data or fabricate analytics results. Then how can we securely process large streams of IoT data at the edge? Our approach is isolating data and its computation within TEE and shield them from the remaining potentially vulnerable edge software stack. Trusted execution environment can support the isolated execution in which code and data are protected. And code and data, it cannot be accessed or modified by the other things out of TEE. TrustZone is ARM's solution for TEE enforcement. It logically partitions the platform's hardware resources into two separate worlds called the normal and secure world. By doing that, the normal world application or even OS kernel in the normal world cannot access the secure world memory or peripherals. For strong isolation, we can only give limited memory into secure world. One notable feature of TrustZone is we can assign I/O to the secure world, which is called the trusted I/O. This can be done by configuring peripherals owned by secure world. By doing that, we can make I/O directly interact with secure world memory. Our approach has two design constraints. First, TCB size should be minimized for the purpose of security. And the second is that the secure memory in TEE is limited. Constrained by these two factors, we'll map three following challenges. First, what functionality should be in TEE and behind what interface? This is very important because porting large functionality incur large TCB, and the wide interface may result in the high potential vulnerabilities. Second, how to execute stream analytics with high throughput and low delay. We need secure processing within limited memory while delivering a good performance. Third, as untrusted components are in analytics, how to verify the outcome. As both trusted computation and untrusted, even complicated edge components participated in analytics, we must verify analytics execution and its outcome. There are two alternative design choices to isolate the application security-sensitive functions within TEE. The first one is to put all the engines and its libraries to TEE. However, this results in substantial TCP growing, which make engine vulnerable. The second approach is partitioning as is, meaning that partitioning application by program analysis and protect only security sensitive part in TEE. While this approach can comparatively reduce the size of TCP, it is unsuitable for existing stream analytics engine as they are not designed for partitioning. Thus, it incurs wide interface as all the sensitive functions have their own separated interface to enter TEE. Also, current stream analytics engine are using hash-based structure and algorithm which mismatches TEE's limited memory. Then, what our design is different from the existing ones. First, we architect a data plan for protection which has very small TCP and narrow interface. Second, we optimize the data plan's performance, challenging the limited secure memory. And third, we verify analytics execution as untrusted parts are still cooperating with the trusted part. So let's take a look at our design of StreamBox-TZ. First, we architect the data plan, which encloses all the analytics data and computations. The data plan is protected by TrustZone TEE, and thus its integrity and confidentiality are guaranteed. As we only have 3 main components in the figure in the data plan can keep TCP size very small, which is only 5K lines of code in our implementation. The components in the data plan are used for computation or verification, which are optimized for stream processing within TEE. We will give more detail on the following slide. We leave the remaining complicated software stack in the normal world, which we call the control plan. The control plan contains all the functions related to the data flow control. For example, scheduling or threading or operator pipelines. By our design, we only appear narrow and shared nothing interface. Conceptually, we only have 4 entry functions. 2 of them are used for data plan initialization and cleanup, and 1 shared by all the trusted computation. The last one is for debugging. We've observed 3 optimization points in secure stream processing within TEE. The first one is parallel execution in a TEE. The stream operator, in fact, has internal task parallelism. For example, group by operator can be implemented by multiple sort and merge, which can be running in parallel. Recall that we leave the stream pipeline and scheduler out of TEE for low TCP, and thus, enclosing all the operators in TEE cannot fully exploit the parallelism. We instead invent a set of low-level stream algorithms in TEE, which is called the trusted primitive. Trusted primitive can build stream operators with higher parallelism because they are single-threaded, stateless, and oblivious to synchronization by design. Moreover, trusted primitives share cache current memory space in TEE in order to simplify data sharing and avoid data copy. Our current implementation has 23 trusted primitives, which can cover most popular stream operators. Second optimization is about TEE memory management. Existing memory management in the streaming processing is not suited to TEE due to its large code base, hash-based structure or algorithm, and relocation overhead comes from its data container. To deal with such problems, we introduce a special data container, which is called the unbounded array. The unbounded array is virtually unbounded and used for storing data among trusted primitive or operator states. It grows in place, which is backed by on-demand paging in TEE. It is append-only buffer in the continuous memory region so that it can achieve a compact memory layout. As it uses a dedicated large virtual memory, It does not incur any relocation overhead and thus enables fast memory allocation in TEE. We've implemented it using only 0.7K lines of code, which is lightweight, as it is 9x fewer than malloc and 20x fewer than J-malloc, which are generally used in stream processing. The final optimization point is reducing the overhead comes from the ingestion. If the ingested data pass through the OS, it should copy data into data plan, which also incurs some crypto overhead, as OS at the edge is untrusted. To mitigate it, we exploit the trusted I/O, which enables direct ingestion to the data plan in clear text, so that we can remove all the overhead comes from the ingestion. As untrusted parts participate in the analytics, we provide verification of edge analytics engine. In fact, tracking the origin of result like a data lineage is insufficient due to its lack of stream semantics. To deal with that, our solution is adding audit record. When the data plan is invoked, it generates the audit record to track all the data flow among trust primitives with stream model awareness. For example, you can track the window ID or watermark used in stream processing. Then the cloud can verify the analytics by symbolically replaying. In this, we note that when the cloud verifies the analytics engine, there is no real computation. It's only just a symbolic replaying. The cloud verifies two things. First, analytics correctness, which is all ingested data is processed correctly. Second, result freshness, which ensures that the pipeline has low output delays. We've implemented StreamBox-TZ on top of High board, which support the programmable TrustZone. For the control plan, we reuse most of the code from the original StreamBox, but add 12.4 thousand lines of code. On the other hand, the data plan is newly implemented from scratch, and that is written by C. We use 6 benchmarks and 4 different versions of StreamBox-TZ for evaluation, but we just show some of them due to limited time. First, we evaluate the security overhead comes from the isolation by comparing 2 different versions of StreamBox-TZ. This version is insecure, in which StreamBox-TZ is completely running in the normal world without isolation. So it does not have any security features, and thus it can show native performance of StreamBox-TZ. On the other hand, StreamBox-TZ on the right side runs data plan within TEE, having all the security features, including trusted I/O. By comparing these 2 versions, we've evaluated the isolation overhead. And finally, we've achieved modest security overhead, which is less than 25%. Second, we evaluate an impact of trusted I/O by comparing a different set of 2 versions similarly. The third version shown at rightmost side does not exploit trusted I/O. By comparing StreamBox-TZ on the center and without trusted I/O on the rightmost side, we can evaluate the impact of trusted I/O. Without trusted I/O, about 40 to 50% throughput loss happens. This is due to data copy and decryption overhead. So now let me conclude my talk. We built StreamBox-TZ, a secure stream analytics engine at the edge, which is designed and optimized for data-intensive parallel computation on minimal TCP. We architect the data plan for protection, leveraging ARM TrustZone, and we optimize its performance within TEE and propose audit record for verifying edge analytics execution. With the following contributions, StreamBox-TZ achieved competitive performance with strong security features. Thank you for listening to my talk, and I'm waiting for your question.
Hi, nice work. Mark Silverstein, Technion. I wonder what is the threat model if you're running part of the streaming logic or processing logic in untrusted? What would happen if the adversary tries to change the logic and modify it? Would that be a valid scenario for protecting it using your system?
So your question is?
My question is, if part of the application logic runs outside of TrustZone, how do you ensure that the application is not attacked?
Okay, I got your point. So that is that can be verified by the cloud verifier, because we tracked all the computation happening in the trusted execution environment. Like the scheduler or pipeline in the normal world, when the scheduler invokes the trusted primitive, the audit record store its primitive ID, and this record can be replayed in the cloud verifier. And by replaying this audit record, it can track whether this pipeline can be compromised or not. So for that, the cloud verifier should keep the copy of operator pipeline. So that's our assumption. Like the cloud verifier has to have the same pipeline.
And this, sorry, just to finalize this question, so the cloud verifier is assumed to be trusted?
Yeah, our Felix model,
right.
Yeah. Thank you.
I have one question. Did you consider an alternative of running a hypervisor inside the TrustZone, which will eliminate the limitations of trusted execution environment for processing the data?
So your question is, can we use the hypervisor or the other security?
Set an hypervisor inside the trusted execution environment and just do the processing outside of it in a different VM, in a sense.
Oh, I see your point. But in my opinion, yeah, it is possible. Like, for example, VTZ support the virtual environment in the TrustZone. But my opinion is like, for to deal with the high velocity stream analytics, data, we have to keep the same memory cache current memory region to speed up the processing. So I think that, of course, that can guarantee the security as well. But I think that in terms of performance, it may be worse than our approach.
Okay. Thank you. Let's thank our speaker again.
Thank you.